This device is called the E over M device, or E over M of the electron apparatus. And the way it works is there's a glass tube here, and inside of it there's a filament that produces electrons by getting really hot, so the electrons just sort of boil off. And then there is an accelerating grid that takes those electrons and accelerates them downward, and you can see a dim green beam going straight down. So hopefully it's obvious, I'll turn the accelerating voltage down and it should go away, and then I'll turn the accelerating voltage back up and you should see the green beam reappear. And so the velocity of the electrons is in the downward direction, and their speed is determined by the accelerating voltage, as we've discussed in class already. And so I'll set this to 400 volts for the accelerating voltage. And the reason that you can see a green beam is because the glass bulb here is filled with a very low density helium gas. And so periodically some of the electrons collide with the helium atoms, and when they do, some of the electron kinetic energy is given up to electrons on the helium. Those electrons will jump from one orbital to another, and when they fall back down, they emit green light. And so most of the electrons continue their pathway downward, but there are enough of them that collide with helium to create the green color so that you can see their path. The helium doesn't really matter. What's really important is that we produce a beam of electrons and that we're able to see it. This apparatus also has two Helmholtz coils, and these coils have some number of wire turns, and when I turn the current on for the coils, a current will go through the coils in some direction, and that's going to create the Lorentz force on these electrons, because these are charged particles with a velocity. And if you recall, the Lorentz force is the charge of the whatever particle is moving. It's that charge times that particle's velocity cross product with the magnetic field, and in this case the magnetic field is that magnetic field produced by these coils. There are two coils so that the magnetic field in between the two coils is somewhat uniform, and it should only go either into the direction the camera is pointed, or it'll be towards the direction of the camera. And so we can figure out what it needs to be, what direction the current needs to go in order to create a force on negative charges so that they deflect into the bulb. So if we think about, there's a velocity in the downward direction, if the magnetic field were to point out towards the camera, that would supply a force on a positive charge that's to the left, and on a negative charge that would be to the right. And so since we need the electrons to go to the left, that direction coming towards the camera for magnetic field doesn't work. If we reverse that magnetic field, then the velocity of the electrons crossed with a magnetic field going toward the direction the camera is pointed would produce a force on positive charges to the right, and on negative charges that would be a force to the left. So that must mean that we need a magnetic field going into the same direction as the camera is pointed. I can turn up the current here and start to visualize that force. So you'll see that the green beam of electrons begins to deflect from the Lorentz force, and eventually, if I turn up the current enough, the Lorentz force continues acting on whatever the velocity of the electron is at different positions. Since it's a uniform field throughout this coil, an electron that's traveling over here down and to the left gets a Lorentz force that is perpendicular to that and the magnetic field that's pointed toward the same direction as the camera. And eventually I'll create a circle that fits inside of the bulb, and I can use the ruler inside of the bulb to measure the size of the circle. So for example, if I turn it till the 7 on the ruler is lit up, that's a 7 centimeter diameter circle. that comes from turning the magnetic field up to produce more force. If I turn the accelerating voltage up or down, we could predict what that's going to do to the Lorentz force, because that's related to the velocity of the electron. So for example, if I turn the accelerating voltage up, I can turn it to some number where it goes to, let's say, 8 centimeters, so that's around 500 volts. Or I can turn it down until the circle goes down to 6 centimeters, which is around 300 volts.